Well, hello, pre-calc. Here's the do now for today. Make sure, as it says in the directions here, that you keep track of this in your notebook. But please go ahead and expand that polynomial x plus x to the power 2 plus x to the power 3 plus x to the power 4 plus x to the power 5 plus x to the power 6 quantity squared. You can use a multiplication box like the one I illustrated, or you can do it some other way. All right, we'll hit pause on the video until you've got your multiplication completed. All right, well, when finished, it should look something like this. So when we're multiplying, those exponents are going to add. So follow-up question, how many of these different double roll combinations would award you a sum of 5 on the dice? Could be a 1 and a 4, like in the little picture over here, but anything that adds to 5. How many different ways? Yeah, well, anything that's got a sum of 5 is going to have that exponent of 5. So there are 4 outcomes that give us a sum of 5. Cool. Well, so today we're going to learn about polynomial modeling. This is the next counting method we're going to learn about in our journey through statistics or fishistics. So polynomial modeling, we have seen some before. Just to set the stage a little bit, a couple of days ago, our do now involved these 2 wheels of fish, as you might expect, for our study of fishistics. And you remember we listed the outcomes for one wheel of fish on one axis in blue, and the outcomes for the other wheel of fish on the other axis here in green. And then we added together to get the total number of fish you would win, right? Which is really not unlike what we just did in the do now today, but we wrote it differently. Right. Well, we've done the similar things where we use an algebraic expression to represent some outcomes. We've seen it with our expansion of h plus t quantity raised to several different powers, right? And so we got these sample spaces as algebraic expressions representing heads and tails. And so just as an example, here's a sample space for 3 coin flips. So inside the original expression right there, the h plus t represent the outcomes for a single event. The exponent right there represents the number of trials. And then when we multiply that out using our algebraic approach, the multiplication boxes or whatever method you use, we get the sample space. And so they were head h to the power 3. They're heads on 3 coins that had a frequency of 1. Coefficient is 1. That tells us there's one possible way that gives us heads on all 3 coins. And 3 outcomes that give us heads on 2 tails and heads on 2 coins and tails on the other coin, and 3 outcomes that give us heads on 1 coin, tails on 2 coins, and 1 outcome that gives us tails on all 3. Right, so we got the sample space completely described, all of the outcomes and combinations described in that algebraic expression. So we've seen this as an example of polynomial modeling. We've seen it before with like categorical outcomes like heads and tails. And so today we're gonna look at how we can use that not only for these categorical kind of outcomes, but also numerical ones. So basic approach remains the same, but there's going to be a couple of differences. So we've actually just seen this in today's do now. So here's what you should write into your notes for today. So a polynomial model is an algebraic approach to find the entire sample space of a repeated event. So for dice, those are a numerical outcome. You get different numbers on the different sides of the die. We're going to represent those numerical outcomes with exponents. And in this case, the variable x really has no bearing on anything. We're just using it as a placeholder to do algebra on. So it's the exponents and the coefficients that are going to have all of the meaning for us. But highlighted in red, those are all the outcomes for one event. That's going to go inside the parentheses. So if for a normal 6-sided die, we're going to have those 6 different terms representing with the exponents representing the different numbers on the die. And then we're going to raise outside the parentheses, we'll raise that to an exponent for however many times we do with that event, the number of repetitions or trials. So for 2 dice, it'd be 2. And then when we expand that, we did the multiplication in the do now today, we combine all the like terms. In blue, you can see that is our sample space. So all the possible outcomes are being represented algebraically. If we just pick one as an example, right there, there are 4 different possible combinations, 4 different outcomes that will give us a sum of 5. Just like you saw when I asked you this follow-up question for the do now. It could be a 1 on this die and a 4 on that die. It could be a 4 on this die and a 1 on that die, a 2 on this one and a 3 on that one, a 3 on this one and a 2 on that one. So there's 4 different possible combinations, right? So that's the way we interpret the different pieces of the algebra expression. The coefficients are the frequencies, so that is the yellow part. And then in magenta, that exponent represents the sum, right? So you add the two dice together. What is the sum? Or we could just call it a value, right? So those are the two pieces we need to pay attention to. The coefficients represents the frequency. The exponents represent the sums. The x really is just a placeholder to keep track of our different algebra terms, to keep the different events separated in our sample space. All right, so if I go back to the table we had from the do now, another tool I can use is to make a frequency table. And so some of you might say, well, I can totally just look at it and see from the original table that I had. I don't need this additional table. But here's what a frequency table does. It can be a really useful thing if you're going to keep using that same set of outcomes for multiple different questions or analysis or whatever. So I just looked at all the different sums, so it'd be the exponents, and listed their frequencies. So there's a sum of 2. If you roll a 1 on each die, you get a sum of 2. Right? There's only one possible outcome that gives you a sum of 2. Right? So the frequency is 1, and then for each of the different sums, it just listed them in the left-hand column along with their frequencies, the right-hand column. Of course, that's the same thing we're going to see if you have combined all the like terms and collected those to give one big algebra expression that describes the entire sample space. Right? Each of these coefficients and exponents correspond to what I've written in the frequency table. So a sum of 3 has a frequency of 2, and we see the same thing in this particular term here. The frequency is the coefficient, so that's the 2, and the sum of 3. So there are 2 different ways to get a total of 3 on your dice. All right. So just to repeat, the exponents represent the value or the total or the sum. The coefficients are the frequencies. So from either that frequency table or from the combined like term version of our algebra expression, we can do a little bit of analysis here. What outcome happens the most? Give me a minute to think. All right, well, the thing that happens the most is going to have the highest frequency. So the highest frequency was 6, but the sum is 7. Or you could see that in the original table, there are more 7s, x to the power of 7, than anything else. So the sum of 7 is going to happen most often. Okay, and then we could do, oops, sorry, I've uncovered too much. Some more things, like find probabilities. If you roll 2 number cubes, what's the probability that the sum of those 2 dice will be exactly 5? All right, well, we kind of addressed this one already. So that one I just circled in purple is the term that we are after, because the exponent is 5. The exponent represents the value or the sum, but that does not show up in our probability fraction at all. We want the coefficient of 4. That's our top number. And then in our probability fraction, we need the total size of the sample space to be our bottom number. And there are 2 dice, each having 6 sides. So we could quickly calculate this. 6 to the power of 2. 6 is the number of outcomes for 1 repetition, for 1 trial, but there are 2 trials, so we're going to raise it to the power of 2. 6 to the power of 2 is 36. Or, scroll back up here, you look at this table, it's 6 spaces across and 6 spaces down. 6 times 6 is 36. Exact same calculation, different explanation. And then, of course, we always reduce our fractions. So 4 over 36, we could reduce that to 1 out of 9. All right, when you roll 2 number cubes, what's the probability that the sum of the numbers will be exactly 10? And we'll see if you can figure this out. I'll give you a second. Exactly 10, so we're looking for the exponent of 10. The coefficient there, that's the frequency, so I want the 3. Still 36 possible outcomes in that sample space. That is not a very good looking 36. And then always reduce our fractions, so 3 out of 36 we can reduce to 1/12. Okay, so if we have some polynomial model, for example, let's say we have some crazy weird die and it's got one side with a 7, 3 sides that show a 4, and one side that shows a 0 on it. We're going to take that funky die and roll it 3 times, add together those 3 rolls. Okay, or maybe this represents something else. I don't know. But if we need to multiply this polynomial by itself 3 times, what are our options? Well, first option is we'll just take the polynomial and actually multiply it by itself 3 times using progressively larger multiplication boxes. So I can list the terms across one edge, the same terms down the other edge, just multiply them together, add the exponents, multiply the coefficients, blah, 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 combine like terms. Gives me x to the power of 4. I've got a couple of different x to the power of 11 terms, so add those coefficients. 3 and 3 is 6. And so on, collect all of the like terms. And then in order to raise this polynomial to the power of 3, I have to multiply this answer I just got by the original polynomial one more time using an even larger multiplication box. Combine all those like terms. I typed it out here so it's a little bit easier to read. Okay, that's kind of a cumbersome approach, right? So while it is the first approach that we have learned, not the one we're going to use most of the time. So we can use some technology to help us. The best option is at a polynomial calculator at this website called Wolfram Alpha. Wolfram is the guy's name. You can see right there, Wolfram is the name of the mathematician that created this website, and it will do a lot of stuff. We're going to use it just to expand our polynomials, because really what we're after at this point in our math career is being able to take the polynomial model and interpret it and apply it to do some statistics work, not get that algebra practice of repeatedly multiplying, which is important, but just not what we're after right now. Okay, so for let's just look at this one at a time here. So for let's say we got this spinner, we're going to spin the spinner 4 times and add together the spins, all 4 of them. All right, so we could create a polynomial model. Okay, so on one spin, what are the possible outcomes? Well, there is one space on the spinner with a 0. There's one space that has a 1. There are 2 spaces that have 3s, and there's one space with a 7. All right, so there's my base polynomial. I'm going to raise that whole thing to the power of 4 for 4 spins added together. Okay, I know you already saw this a second ago, but before we go any further, let's calculate the size of the sample space. The size of the sample space, right? Well, 5 spaces on that spinner, 4 repetitions. So 5 to the power of 4 is going to tell me the size of the sample space. So I can grab my calculator real fast here. 625. Oop, where'd the pen go? Pen, right. And typing in that polynomial model into Wolfram Alpha, I got the following result. So here's the entire sample space, everything possible for 4 spins, all the different possible combinations. There's a lot of them, 625 different possible combinations, right? So just pause for a moment to appreciate this. Like if we were going to make some sort of outcome table, like this would be a ridiculous amount of work, right? To come up with all 625 different possible combinations of how you could spin the spinner 4 times and add them up. Okay, that's absurd to try to do that by hand. So we've got some more sophisticated approaches. We can use technology to help us, but it's not just like, oh, look what we can do, and we're going to answer some questions. It's like that represents a huge amount of time saving and work saving, and that's a pretty big deal. All right, well, what is the most likely number of fish? Here's our interpretation question. What is the most likely number of fish? So if we go back to the expanded polynomial model, we're looking for the biggest coefficient, which I think is right here. So the biggest coefficient means it is most likely to happen. That has the highest frequency. But the question doesn't ask for the frequency. It wants to know the number of fish. That's the sum. So 10 is the exponent. That is the number of fish. But if I had asked what is the probability of getting 10 fish, the probability of getting 10 fish, I'm going to use that 60 as the frequency, and the size of the sample space was 625. And then as always, we can reduce. So, sorry, you can't always reduce, but as always, if you can reduce, you should. This one we can reduce, so divide them both by 5, so I'm going to get 12, 125.